Welcome to Cosmos in a Pod Space and Astronomy series, Episode 1. Are you ready to tackle some of the biggest questions out there?
I think so.
I hope so, because today we're diving deep into the origin of the universe itself.
That's right. We're talking about the Big Bang, which is, as you probably already know, the prevailing theory for how everything we know and see came to be.
I think most people have heard about the Big Bang, but when I hear those words, to be honest, my mind just goes straight to an explosion.
Right.
Is that really an accurate picture?
It's a common misconception, but it's way more nuanced than just an explosion. Think of it more like an incredibly rapid expansion of space itself from a super, super hot and dense state. We're talking about a state where all matter and energy in the universe, like everything, was packed into a single point.
All the matter and energy in the entire universe was in a single point.
That is a pretty big concept to wrap my head around. It is. And that leads us to this idea of a singularity, which is a point of infinite density and temperature. It's a realm where our current understanding of physics just breaks down. We're talking about a time before space and time, as we know them, even existed.
Infinite density. No space or time. Okay, yeah, you're already pushing the boundaries of my imagination here. So how do we go from the singularity to, well, a universe?
Well, about 10:43 seconds after the singularity, a time frame that's known as Planck time, the universe just started expanding and cooling at an almost unimaginable rate.
So that's the bang part.
Exactly. But instead of picturing matter exploding outward into space that already exists, imagine space itself expanding. The universe went from subatomic size to macroscopic in basically an instant.
Hold on. Instantaneously. We're talking like faster than the speed of light, right?
Yeah, so the laws of physics as we know them, like the speed of light, didn't really work the same way in those very, very, very first moments of the universe. We're talking about a super unique set of circumstances.
Wild. Okay, so while all this is happening, what's happening to all that matter and energy packed into the singularity?
As the universe expands and cools, energy starts transforming into particles. So first, we get the basic building blocks of matter, quarks, and gluons. Those eventually combine to form protons and neutrons, the things that make up atoms.
Right. So we're finally seeing the ingredients for everything.
Exactly. And about 380,000 years after the Big Bang, the universe cools enough that protons and electrons can finally come together and form neutral hydrogen atoms.
So things are finally starting to, calm down a bit.
Yeah, you could say that. This moment, called recombination, is super important. Before this moment, the universe was like a dense fog that was completely opaque to light. But after atoms formed, light could finally travel freely.
And is that light something we can still actually observe today?
Yes, we observe it as the cosmic microwave background radiation, or CMB. It's basically a really faint afterglow of the Big Bang, like a baby fire of the universe from when it was just 380,000 years old.
Okay, so we have this CMB, which is light from the early universe. But how do we actually know that the Big Bang happened? We're talking about events that occurred billions of years ago. How could we possibly have evidence?
It's a great question, and the answer lies in a few key pieces of evidence. The CMB itself is one of the strongest pieces of evidence. Discovering it in 1965 completely revolutionized how we understand the universe. The patterns and temperature variations in the CMB align perfectly with what the Big Bang model predicts.
So by studying the CMB, scientists are essentially looking back in time to the early universe.
Yeah, that's a great way to put it. But there's even more. Remember how we talked about the universe expanding? Well, in the 1920s, an astronomer named Edwin Hubble observed that galaxies are moving away from us, and that the farther away they are, the faster they move. This observation, called Hubble's law, strongly suggests that the universe is expanding, just like the Big Bang predicts.
So Hubble's observations are like actually seeing the expansion billions of years after the Big Bang. What else supports this theory?
The abundance of light elements like hydrogen and helium in the universe. The Big Bang theory predicts that these elements would have been formed in huge quantities in the first few minutes after the Big Bang, and when scientists measured the abundance of these elements, they found a remarkably close match to what the theory predicted.
So the amount of hydrogen and helium acts like a fingerprint, pointing right back to the Big Bang. That's three really compelling pieces of evidence. The CMB, the expanding universe, and the abundance of light elements. It's hard to argue with that. But there's this one question that just keeps popping into my head. If the Big Bang was the beginning of the universe, then what was there before the Big Bang?
Yeah, that's the question, isn't it? And to be honest, it really pushes the boundaries of what we know right now. The Big Bang Theory explains how the universe evolved from that moment of expansion onward incredibly well. But what caused the singularity to be there in the first place? What existed, if anything, before it? Those are still big mysteries.
So we're basically looking back at the first page of the universe's story, but we have no clue what came before. Are there any theories that even try to address that?
Oh, yeah. There are some theories out there, and they are some of the most, mind-bending ideas in all of cosmology. One concept is the multiverse theory. It says that our universe may just be one of many, many universes, this vast multiverse. And each of these universes could have its own set of physical laws and maybe even its own unique origin story.
So you're saying there can be a bunch of universes out there that are totally different from our own?
It's a pretty crazy concept, yeah.
Yeah.
Another idea is something called quantum fluctuations. This gets into some really complex quantum physics, but the main idea is that these random fluctuations in a quantum vacuum, which is essentially nothingness, could have somehow created the singularity, and that sparked the Big Bang and the creation of space and time as we know them.
So something came from nothing. Trying to imagine that one.
Yeah, it definitely challenges how we normally think about things. Then there are cyclic universe models, which say that the universe goes through these endless cycles of expansion and contraction. In those models, the Big Bang isn't a one-time event. It's more like one stage in this huge cyclical process.
So the Big Bang could be just one chapter in a never-ending story with no beginning and no end. These theories are intense. Okay, I have to ask. If the universe is always expanding, what's it expanding into? What's outside the edge of the universe?
Another good question, and it's one that usually leads to some confusion. It's totally natural to think of the universe expanding like a balloon inflating in a room. But it doesn't really work that way. The Big Bang wasn't matter exploding into space that already existed. It was space itself expanding. And the universe, it doesn't have an edge or a center. Every point in space is moving away from every other point, and there's no outside.
Okay, so the universe isn't expanding into anything. It's just getting bigger. I don't know if I could even picture that.
But it's tough to grasp, right? Because we're so used to thinking in 3 dimensions. But the universe is way more complex than that. Now, you might be wondering, if everything's moving away from everything else, does that mean our galaxy, the Milky Way, is also moving away from other galaxies?
Yeah, actually. Are we on our way to being alone out here in the vastness of space?
Well, not exactly. Most galaxies are moving apart, that's true. But gravity is still a major player here. Gravity holds galaxies together in these clusters, even while the space between those clusters is expanding.
So it's like this cosmic tug of war between the expansion of the universe and gravity. Who's going to win? Is the universe going to keep expanding forever, or will gravity eventually pull everything back together in some kind of like reverse Big Bang?
Another great question, and it's been puzzling cosmologists for decades. For a while, people thought that the expansion of the universe would slow down because of gravity, maybe even leading to a big crunch, which is the opposite of the Big Bang. But then, in the late 1990s, astronomers discovered something really surprising.
What did they find?
They found that the expansion isn't slowing down, it's actually speeding up.
Speeding up? You mean things are moving apart even faster now? I don't get how that's possible. What would cause that?
It's a huge mystery in cosmology. Scientists think there must be some unknown force driving this acceleration, and they call it dark energy.
Dark energy. That sounds kind of ominous. What exactly is dark energy?
That's the thing, we really don't know. We can see what it does, but its nature remains a mystery. We do know that it makes up something like 68% of all the energy in the universe, and it seems to act against gravity, pushing things away instead of pulling them in.
So dark energy is kind of like anti-gravity, the rebel of the universe.
You could say that. But even though it's so important, dark energy is one of the most baffling puzzles in science. And there's another twist. Remember how we talked about matter and energy making up the universe? Well, it turns out that all the matter we can actually see, the stuff that makes up stars, planets, and us, is only about 5% of the universe's total energy.
Wait, so everything we can see, all the galaxies and stars and everything, is only a tiny fraction of what's really out there?
Exactly. Most of the matter in the universe is something we can't see. We call it dark matter.
Okay, another cosmic mystery. So what is dark matter? If we can't see it, how do we even know it's there?
We know it's there because we can see how its gravity affects the stuff we can see. Dark matter doesn't interact with light, so telescopes can't see it. But we can see its gravitational influence on galaxies and galaxy clusters.
So we can't see it, but we can feel it. That's amazing. How much of the universe is dark matter?
Right now, scientists think that dark matter makes up about 27% of the total energy in the universe, and it plays a critical role in the formation of galaxies and the overall structure of the cosmos.
So even though it's invisible, dark matter is actually shaping the universe all around us. It's pretty humbling to think about how much we still don't know about the universe.
It really is. These mysteries, dark matter, dark energy, the singularity, they're all at the forefront of what cosmologists are studying. They really challenge us to come up with new ideas.
Yeah, my brain is definitely a bit fried after all this talk about the universe and all its mysteries.
Yeah.
But wow, it's just incredible.
It really is. And honestly, we've only scratched the surface. There's just so much more to learn.
Welcome back to Cosmos in a Pod. We've talked about a lot in our exploration of the Big Bang, from the singularity to the expansion of the universe, dark matter, and even dark energy.
Yeah, it's been quite the tour of the cosmos.
It really has. So now I'm super curious about, like, what's next? What are the big questions that are really stumping cosmologists today? What are they most excited about researching?
One of the hottest areas of research right now is studying the very, very early universe, those first moments after the Big Bang. Remember how we talked about the cosmic microwave background radiation, that baby picture of the universe from when it was only 380,000 years old?
Yeah, it's like a little glimpse back to the universe's baby days.
Exactly. With all the advancements in telescopes and technology, scientists are able to study the CMB with crazy precision these days, and they're looking for any little patterns or variations that could tell us what happened even earlier, maybe even fractions of a second after the Big Bang.
So we're talking about getting closer and closer to the very beginning of time. That's amazing. What kind of things are they looking for in the CMB?
One of the most exciting things is the search for evidence of something called inflation. Inflation theory proposes that in the first tiny, tiny fraction of a second after the Big Bang, the universe expanded unbelievably fast, way faster than how it's expanding today.
So inflation was like the Big Bang, but on fast forward. Why do scientists think that happened?
Well, inflation helps to explain some of the weird things we see about the universe today. For example, on large scales, the universe looks incredibly smooth and uniform, and that's tough to explain without some period of rapid inflation to smooth everything out.
So inflation helps to solve some of those cosmic mysteries. Are they actually finding any evidence for it in the CMB?
They're looking for really, really specific patterns and variations in the temperature and polarization of the CMB. Inflation theory says those patterns would have been imprinted on the early universe. There have been some really interesting hints in recent years, but it's definitely still being researched.
It sounds like studying the CMB is kind of like doing cosmic archaeology, digging through these faint leftovers from the early universe to understand its history. What other tools and techniques are cosmologists using to study the early universe?
One of the most powerful new tools is the James Webb Space Telescope, which we talked about a little earlier. It's specifically designed to observe infrared light, which can actually see through dust and gas, so it can see things in the early universe that are hidden from other telescopes.
So it's like having a whole new set of eyes, letting us see deeper into space than ever before.
Exactly. And it's already giving us some awesome images and data that are changing how we think about galaxy formation, how stars are born, and how the early universe evolved.
Wow, that's just incredible. Are there any other new groundbreaking telescopes or experiments coming up?
There are a bunch. Another really fascinating area is detecting these things called gravitational waves. They're basically ripples in space-time that happen when massive objects like black holes or neutron stars accelerate.
Gravitational waves. It sounds like something out of a sci-fi movie.
Right, but they're absolutely real, and they offer a completely new way to look at the universe. Up until pretty recently, we could only study the universe using electromagnetic radiation, things like light, radio waves, X-rays, and all that. But gravitational waves, they carry information about objects and events that we can't see with regular telescopes, things like when black holes collide or even from the very first moments of the Big Bang.
So we're not just looking at the universe anymore, we're listening to it too. That's wild. What do we actually learn from these gravitational waves so far?
Well, the first time we detected gravitational waves back in 2015 was a huge deal. It confirmed this big prediction from Einstein's theory of general relativity. And since then, we've detected dozens more of these gravitational wave events, and they've given us insights into how black holes act, the characteristics of neutron stars, and what goes on in the most extreme places in the universe.
It's crazy to think that now we can observe the universe in these two totally different ways, using light and using gravitational waves.
Yeah.
What kind of new discoveries do you think are possible when we combine those?
It's a super exciting time to be studying cosmology. By combining information from regular telescopes, the James Webb Space Telescope, and gravitational wave detectors, we're getting this much richer picture of the universe. We're starting to really understand how stars and galaxies are born and how they change, how black holes interact, and how the universe itself has transformed over billions of years.
It sounds like we're right on the edge of a whole new era in astronomy and cosmology.
I think so too. And who even knows what incredible things we'll find? We might discover new particles, new forces, or even new laws of physics. Maybe we'll finally get close to answering those really big questions about how the universe began and what reality actually is.
I can't wait to see what the future holds. This has been a fantastic deep dive into the Big Bang and all the mysteries of the universe. Thanks for taking us on this journey.
It's been my pleasure.
And to everyone listening, thanks for joining us on this wild ride through space and time. Make sure to subscribe to Cosmos in a Pod for more mind-blowing deep dives into the universe. And until next time, keep looking up and never stop asking those big questions.